Okay, so let's start at 5.3. The objective for all this is students will understand the basis for the quantum mechanical model of the atom, so I want you to write that down. But I also want you to write these down in the margins as well. Okay, I want you to be able to answer these questions by the end of this lecture and by the end of your reading. How are the wavelength and frequency of light related? I do also want you to be able to answer these questions by the end of 5.3. How are the wavelength and frequency of light related? What causes atomic emission spectra? How are the frequencies of light an atom emits related to the changes of electron energies? And finally, how does quantum mechanics differ from classical mechanics? All four of those things you should be able to answer by the end of this section. Okay, so this is the quantum mechanical model. Light travels by waves similar to waves moving a boat. Okay, light waves are actually electromagnetic waves and a very small portion of the total spectrum. The spectrum is huge. Okay, if you look off to the right of my classroom, you see a spirally spectrum poster over there. Just the very slightest bit of it at about 1 o'clock on the circle is the visible light. Everything else are the other kinds of electromagnetic radiation. Okay, now we have certain characteristics of wave. The first one is the amplitude, which is wave height, which is the distance above the center line to the crest or the trough of a wave. The wavelength, which is the distance between crests. Here's the crest. Okay. Velocity, which is how fast waves move past a point. So they have amplitude, wavelength, and velocity. Okay, now, they also have frequency. However, frequency is inversely proportional to wavelength based on the velocity of the wave. So, we have the equation determining the relationship between wavelength and frequency is this, where C equals lambda, which is our wavelength, times F, which is our frequency. This is also frequently written as C equals H nu. This squiggly V is a Greek letter called nu, and it is another variable for frequency. Sorry, I gave you the wrong formula for that. That is not H nu. It is lambda. Lambda nu. And lambda is the wavelength, nu is the frequency. Okay. Now the electromagnetic spectrum, okay, the amplitude determines the intensity or the concentration or the brightness or the loudness of the wave. And so, if bright light and loud noise are both, can be both equally annoying, or can both be annoying to people if they're too much. That's because the amplitude of the wave is very large. Now, the shorter the wavelength, the more energy it has, and the more penetrating the ray. Okay? Gamma rays are about 10 to the negative 11th meters, where radio waves are 10 to the negative 1st meters. So about a decimeter long is a radio wave. That's why if you go under bridges, radio waves often can't pass through, at least not AM wave. Okay. Visible light, or the white light that comes from a light bulb, or that comes from the fluorescence overhead. Okay, they actually have an infinite number of colors in it. Okay, but it's generally characterized as Roy G. Biv. And there's an interesting story that about Isaac Newton with Roy G. Biv. Roy G. Biv stands for red, orange, yellow, green, blue, indigo, and violet. Now, the reason indigo is in quotes is because of the story by Isaac Newton. So, sit back and hear a tale. Isaac Newton was a very devout Christian, as well as a as a phenomenal scientist and one of the big three in my pantheon of smartest men of all time. And however, because he was a devout Christian, he could not morally accept the fact that there are really only 6 colors. And he invented the color indigo to come up with a 7th color, because 7 is a much more biblically friendly number than 7. I'm sorry, than the 6 colors. However, we all know that there are 6 colors, and because of the complementary colors that we have, we've got red, orange, yellow, green. Select my blue, please. Select blue. There we go. Blue and violet. And those are 6 primary colors. And we have these, these connections here, for our complementary colors and that sort of thing. And there's no room for a 7th color. There's no I in here. That's silly. There is no room for that extra color. So Isaac Newton completely fabricated it just so that he could have a 7th letter. So really, this should be, instead of Roy G. Biv, it should just be or Roy G. Biv rather than Roy G. Biv. Okay, so that's Isaac Newton. Really smart guy, but sometimes he fudges his data. Now, these colors are fractionated out with a prism, like raindrops, which make a rainbow, or, dare we say, a double rainbow, all the way. Now, our visible spectrum runs from about 400 nanometers, which is in the violet range, to 700 nanometers, which is in the red range. Okay, and which is still just a very, very small amount of our electromagnetic spectrum. Now, back in section 5.1, we talked about the bright line spectrum, or the barcode of a particular element, and we will be doing an experiment on it, or we'll be doing a demonstration on that if we haven't done it already. The bright line spectrum is a spectrum. Now, mind you, spectra is plural for spectrum. A spectrum that only contains certain colors or wavelengths. And every element, when heated, has a particular unique line spectrum, much like that of a barcode, which can be used to identify an element. And these line spectra are developed using what are called diffraction gradients, which are used to actually come up with the different elements. When we have time, I need you guys, I want you to write this in your notes, and I want you guys to remind me about the Big Bang Theory. Because this particular property of elements led to the discovery of the origins of the universe. Okay, which moves us on to Planck's theory. Max Planck, not Planck, Planck. Max Planck in 1900 accurately predicted how the spectrum of an object changes with its temperature. And the relationship is this: the energy an object has equals h, where it is his own constant, times nu, which is the frequency of the radiation. So E is the amount of energy absorbed. H is a very, very small constant, 6.6262 times 10 to the negative 34th joule seconds. And the frequency, and this nu, there's that nu again, is the frequency of the radiation emitted. Now, Planck's theory proposed that the energies absorbed or emitted by atoms are quantized. In other words, their values are restricted to certain quantities. They're sort of like M&Ms, where instead of having this huge vat of chocolate, you take a little bit and wrap it in candy, and it is called an M&M, where it is a very specific amount of chocolate. That is what light is like. Light comes in quanta. They are little specific amounts of energy called quantums okay, or a quantum is a single amount of energy, and plural they are called quanta. And Einstein used this equation to explain the photoelectric effect, which is actually what he won his Nobel Prize for. He did not win it for relativity, he won it for the photoelectric effect, which in the long term might actually become more useful than relativity. He called these pieces of energy photons, which are tiny particles of light. And the photoelectric effect is this. When he would shine light on a metal, sometimes sodium, it ejects electrons from the metal, which can then be used to produce a small electric current. Now, this happens in violet light, but not red light, even if the red light is intense. Why is that? Well, remember that our relationship is E equals H nu. And nu is only about the frequency of light. Well, violet has a much greater frequency than red. Red has a much lower frequency, which means that violet light is containing more energy, and that's going to cause the electrons to eject from the metal rather than a red light, which won't. Okay. It also brings us to Heisenberg's uncertainty principle. The position and the momentum of a moving object can never simultaneously be measured or known exactly. Now, some sports geeks say that this is why certain hitters can't hit a curveball, but I think it's just because they can't adjust to a curve and they're not expecting a fastball and they can't adjust to a curve. However, that's beside the point. Now, this is interesting because this is why we have to go look at the regions of space where electrons exist. And so because we can never really know where an electron is or where it is going, which is sort of what this has in mind. The position is where it is. And the momentum is where it's going. Okay. So the position is where it is. That's ugly. I'm going to need to rewrite that. Where it is. And the momentum is where it's going. Okay. We can never know both of them exactly. If we measure where a particle is, okay, we have absolutely no clue as to where it will go next. And vice versa, if we know where it is going, okay, or in other words, what momentum it has, we have no idea where exactly it is. Okay, we could just say, well, we know it's headed that way, but we don't really know where it is. Okay? And this is the end of chapter 5.3, and you guys should be able to get through this and move on to the homework for this. And so that's your homework. It's going to be section 5.3, and those numbers, which brings you back to number 4. It's actually homework number 4 right there on the list. So we adjust the due dates a little bit. I'll have you guys do number 6, and we will delay that for another couple days. So 5.3, and then you guys have your lecture, and you guys can review this over and over again on the website. See you in class.